Welcome, this is Mrs. Nearing, and I'm going to talk through some of the buffers textbook problems here, and I'm just going to talk through the setup. I'm not going to give the actual numerical answers because you can find those in the textbook. So let's take a look at problem number 29. So we're trying to find the pH of a solution, and we'll notice all these solutions are buffer solutions, which, the name of the homework may have given that away, but the way that you recognize that you have a buffer is when you have a weak acid and its conjugate base. And the generic formula that we sometimes use for a weak acid is just HA, where A stands for some generic anion. And then the conjugate base, the way you find the conjugate base is by removing a hydrogen from the acid. So if I remove a hydrogen, what's left is A. And since originally this was neutral, once I take a positive hydrogen away, this now has a -1 charge. So that's just a generic example of when we have a buffer. And when you have a buffer, there's two ways in which you can do a pH calculation. You can set up an ice chart and use a Ka or a Kb expression, just like you would with, weak acid or weak base calculation. The difference with the buffer is you're going to have starting values for both HA and A- in your K expression. The other option you have for a buffer is you can use this equation, pH equals pKa plus the log of A- over HA. This is known as the Henderson-Hasselbalch equation. This equation you can only use for buffers. So this one is for buffers only. If you're trying to solve for pH and you don't know the molarity of HA and A-, you can't solve. So you can only use this if you have a given amount of HA and A- in your solution. This top equation you could use for a weak acid or for a buffer. So this one's a little more universally applicable. So just be careful with the Henderson-Hasselbalch, only use that for buffers. So if you look at these setups in problem 29, these are all buffers. There was a table with Ka values. I've already gone through, written all the relevant Ka values down next to the problem. But we've got this first solution. It is a solution of, this is formic acid and sodium formate. Whenever you see an ionic compound like this, I know it's ionic because there's a sodium in it. So if I got metal and some nonmetals, it's ionic. Keep in mind, aqueous ionic compounds are actually going to split apart into their ions. So I know sodium has a +1 charge. That means everything else here must be my polyatomic anion with a -1 charge. And then you might notice, look, I've got HC2HO2 and then CHO2 minus. This looks like a conjugate acid-base pair. I can tell that because if I take a hydrogen away, I get this guy right there. That must be the conjugate base of my weak acid. And I can do this. Again, I've got two options. I can use an ice chart or I can use Henderson-Hasselbalch. I'll probably set this up using Henderson-Hasselbalch. So this is going to be pH equals pKa, and the pKa is the negative log of the Ka value. Make sure you're using the Ka of the acid in the pair. The acid is the one that has more hydrogens. And then you're going to add the log of your A-, that's 0.15 molar, over my HA, which is 0.2 molar. So that's all I do to find the pH there. Taking a look at part B, I can use the same equation because, again, it's a buffer. In this case, my buffer is NH3 and NH4. Because this right here is an ionic compound made up of NH4 ions and Cl- ions. Cl- is just going to be a spectator, just like up here, in my earlier problem, sodium was a spectator. So these are my spectator ions. So this is my buffer, NH3 and NH4. In this buffer, NH4 is the acid. And again, I can spot the acid because the acid is the one that has more hydrogens. So if I'm going to use my Henderson-Hasselbalch equation, pH equals pKa plus log A over HA, I need to make sure I'm using my pKa value. And if you looked at the table, they typically tend to give you the Kb value of NH3, but not the Ka of NH4. So we have to do an extra step here where I'm going to convert the Kb into a Ka, and I can do that because for a conjugate acid-base pair, Ka times Kb equals Kw. So that means the Ka of NH4 times the Kb of NH3 equals the Kw, which is the one of water. So I'm going to convert that. So that's what I did right here. I found my Ka is 5.6 times 10 negative 10. So I'm going to take the negative log of that number That is my pKa. And then log A over HA. Remember, my acid is the one that has more hydrogens, so my acid goes on the bottom. So NH4 has more hydrogen, so it's 0.22 molar NH4. The one with fewer hydrogens is my base. That one goes on the top. So that's how I'm going to set up that problem there. So problem 33. Notice that, let's look at what we have going on in problem number 33. So in part A, we have just pure HF. So what we have here is a pure weak acid. And what weak acids do when you put them in water, they dissociate. They make H plus ions. So when I'm solving for the pH of a weak acid, this is what my setup is going to look like. And I'm going to solve for X. It's going to give me the hydrogen ion concentration, and I will take the log of that to get the pH. So that is a weak acid problem, which you're probably fairly comfortable with. Looking at B, first one, keep in mind, okay, this is sodium fluoride. This is an ionic compound. So when I put it in water, I have sodium ions and fluoride ions. So sodium, not a hydrogen giver, because there's no hydrogens to give. Not likely a hydrogen taker, so it's going to be a spectator. F minus, hey, that looks like the conjugate base of HF. So F minus is going to be a weak base because it is the conjugate of the weak acid HF. So what does a weak base do? Well, when you put it in water, it's going to be a hydrogen taker, so it's going to make HF and OH minus. And then we can set up a nice chart here and say, okay, this is 0.15 molar F. I'm going to ignore water because it's liquid, so I leave it out of my K expression. I'm going to use up some F minus, make some product over here, 0.15 minus X, X, X. When I set this up, I need to notice that this is a base reaction, so I need to use the Kb value of F minus to solve here. So in order to find the Kb of F minus, I'm going to use this conjugate acid-base relationship we just talked about. So I'm going to take the Kw divided by the Ka of HF. That will give me the Kb. And then I can set up my, I can plug in my numbers. So I'm just going to say Kb. I don't know what that number is off the top of my head. But it's going to be x squared divided by 0.15 minus x. You're going to solve for x. That'll give you the hydroxide concentration. And you can find pH from there. So solution A, you want to recognize, hey, that's a weak acid. Solution B, that is a weak base. It's the conjugate of my original weak acid. And then solution C is a mixture. So let's take a look at this one. Solution C says we mix together 0.15 molar HF and 0.15 molar NaF. And the key thing in this ionic compound, we want to recognize that sodium is actually a spectator. So really what we have is 0.15 molar HF and 0.15 molar F minus. Hey, that looks like a weak acid in its conjugate base. So that right there looks like a buffer. And there's two ways in which I can solve for the pH of a buffer. I can use the Henderson-Hasselbalch equation, which we just talked about up there. And if I use that one, pH equals pKa plus log A over HA. We will find that if these are both 0.15 molar, then I end up with the log of, this value being the log of 1, which is 0. So what that means is if the weak acid and the conjugate base are the same molarity, the pH equals the pKa. So to find the pH, all I have to do is find the pKa of my acid. The other way I can do is I can say, okay, I solved this equilibrium system. So HF is split into F and F minus. And I'm going to set up my ice chart just like I did in this problem over here in part A, except instead of starting with just acid, I'm going to start out with both the weak acid and the conjugate base. And I'm just going to set it up like this. This is what we call a common ion problem, which we saw in KSP problems as well. And I'm going to plug these into my Ka expression. And when you do that, you'll notice it'll be x times 0.15 divided by 0.15. So, hey, 0.15 cancels out. So basically my Ka equals x, which is my H concentration. Therefore, my pH equals my pKa. So two different ways to look at that. All right, and that's all we have time for now.